Dear students, in the previous lecture we have discussed about the RTD and the functions and where we can use it and how it converts from one energy to other energies, what are the input, what will be the output. So in detail we have discussed and what are the metals we can prefer for RTD, everything we have discussed in the previous video sessions. And now in this video session we are going to cover about that how this thermoelectric transducer is going to work, what will be the input quantity, what is output quantity for this thermoelectric transducers. We will see that in detail about the thermoelectric transducers. This thermoelectric transducers, it is a device which converts a temperature into electrical energies. It is not like a RTD. RTD is a device to convert the temperature directly into the corresponding resistance values. That is nothing but the electrical parameters. Here, this thermoelectric differs from RTD. Temperature, actually it is not a temperature, it is a thermal energy. It is going to convert into electrical energies. Thermal energy is nothing but it is called heat energies. So the heat energy is going to convert into electrical energies. That is a actual conversion happening for thermoelectric transducers. We can commonly use thermocouple as a thermoelectric transducers. This thermocouple can be worked based on three basic phenomena. The first one is the Seebeck effect, Peltier effect, Thomson effect. So these three phenomena will be the basics for the operating of thermocouples. Let us see this phenomenon one by one. Now this thermoelectric phenomenon depends on Seebeck effect, Peltier effect and Thomson effect. Let us see first what is the Seebeck effect. The Seebeck effect is a phenomenon in which a temperature difference between two dissimilar electrical conductors or semiconductors produces a voltage difference between the two substances. We have three figures. The first figure is related to Seebeck effect and Peltier effect. Second figure, third figure is explaining about the Thomson effect. So come to the first figure. In this figure we can see we have two metals, metal A and metal B. Both the metal will be joined together and it form a two junctions, junction number 1 and junction number 2. And if junction number 1 is maintain a temperature, high temperature, that is a hot temperature, and junction number 2 is maintaining a temperature just reverse to the junction number 1, it should maintain a temperature of cold. So that means that two dissimilar metals join together and maintain at two different temperatures. So this condition, if we measure, that means if metal 1 has been cut into two halves, and in that gap if I measure, I can get a potential difference between the 2 points. So Seebeck effects directly says that whenever two different metal join together and it will maintain at two different temperatures at the two different junctions, a potential difference will be created in the metals, and that potential difference you can measure by using a voltmeter or galvanometer or any permanent magnet moving coil. That is a concept explained by Seebeck. Now come to the Peltier effect. The Peltier effect is a temperature difference created by applying a voltage between the two electrodes connected to a sample of semiconductor material. Peltier effect is just a reverse of this Seebeck effect. Peltier effect says that whenever two dissimilar material join together and form two junctions, here junction number A and junction number B, and one of the metal has been cutted and electric potential has been passed to this metal. So this potential is a DC voltage. So the current starts to flow into these metals. So it will reach the junction number 1, and the first junction when it will reach us, the heat will be get absorbed. So this junction will be made as a cool, and then the current will start to continuous. It will reach the junction number B, and when the junction number B the current reaches, the heat will be get dissipated. So this junction will be taken as a hot junction, and then the current will flow to its path. So Peltier effect says that when two dissimilar metals join together and it is exited by a supply, then the junction of these two metals will be get at two different temperatures. One junction will be get hot, another junction will be get cooled. So this is called Peltier effect. The third effect will be called as a Thomson effect. The Thomson effect says that whenever a current flows through an unequally heated conductor, heat is evolved or absorbed through the body of the conductors. For example, we can take this as one conductors, and the conductor will be having the two ends. This is the one and another end. So end one is maintained at the temperature of T1, and end two is temperature T2. And let us take that T1 will be greater than T2 because this T1 will be heated. That means this conductor point will get heated by a source. So the T1 definitely will be going to be greater than the T2. So whenever the T1 is greater than T2, that condition, if a current is passed between this end to this end, so this conductor will absorb the heat. The heat will get absorbed if the current is going to pass to the conductor from this end to this end. So this phenomenon will be called as a positive Thomson effect. So suppose if the current is going to pass from this end to this end, the same condition, T1 is going to be greater than T2, maintaining the same conditions, T1 is greater than T2, and the current is going to pass from this end to this end. That means the conductor will dissipate the heat, or it is going to liberate the heat. So that phenomenon will be called as a negative Thomson's. So this is the Thomson effect. Now in the previous slides we have seen what is by the various thermoelectric phenomena. So in order to perform the thermoelectric phenomena, we need to join the two dissimilar metals together. For example, you can see that copper constantine and iron constantine, chromal aluminum, chromal constantine, platinum rhodium, and tungsten molybdenum, tungsten gallium. So these all the categories will be having identification thermocouple. So if it is a T, then it will be a copper constantine, J, iron constantine, so like that. So every combination of this material will be having operating ranges. That is, a copper constantine will operate in -250 to 400 degrees Celsius. Similarly, for every combination we will have the various operating ranges. Now we can see here a practical thermocouple circuit. So in this circuit we can see one of the heater is there. Assume we can take this as a water heater in which we are going to use in a day-to-day life. So whenever when you on this heater, the resistive element is going to be heated. So now this is a thermocouple. So metal number 1 and metal number 2 join together, and one junction. This is the junction number 1, and this is the another junctions. So junction number 1 is connected to the heaters. So obviously it is going to maintain the hot temperatures. The other junction will be get not heated. That means that this temperature of the other junction is going to be lesser than the T1. So this is the other junction where we are connected to the voltmeters. So one junction is maintains the hot temperature, another junction is not maintaining the hot temperature. So this will create a potential difference, and that can be measured by using this permanent magnet moving coil. That is nothing but a voltmeters. Now this thermocouple will be having a much more advantages. If you see the advantages, it will be having a very wide operating ranges that between a -270 to 2700 degrees Celsius, and also the response of this thermocouple will be much more high, and also the accuracy. And even if you have any problem with this thermocouple, also it can be calibrated in the easiest manners. But apart from that, we have so many drawbacks. The major drawback, you can see that we are not getting the temperature characteristics corresponding EMF. So if we draw the characteristics between the EMF and the temperature, it is not a linear one. So that means if temperature varies also, we are not getting the sometimes EMF, corresponding EMF. So there is a major drawbacks. And also we have to maintain the two different temperatures. So maintaining at two different temperatures, it is a really challenge one, because you see in this diagram itself, we are getting the temperature heated. So if how much it get heated, corresponding reversely we have to maintain the cold. If we are not able to maintain the cold, we are not going to get the two different temperatures. So we are not going to get the proper electrical potential. We may get, but we won't get the accurate value. And also we will get the stray voltage pickup is also possible. That means that we will have some interference of unwanted voltage, so that we will get the error value in this voltmeter. So these are the few drawbacks of these thermocouples.